Hello, welcome back. You may recall last year in calculus we found the area under a function using rectangles measured from the top of the function to the x-axis. So in other words, if we have a function, here's the x-axis and there's my function. So if we have a function, let's say f of x, and we want to find the area between a and b, we were able to calculate the area or approximate the area using a Riemann sum. So the width of the rectangle we said would have to be delta x sub I, where I is like a rectangle. We'll talk about that in a second. And the height of the rectangle is at some I value, some x sub I value. We can approximate the area by summing the number of rectangles that we have. Now the area of each rectangle would be the value of the function, the height, times delta x sub I, the base of the function of the rectangle, and we would let I go from 1 to n, where n is the number of rectangles. And this is how we were able to approximate it. To get the exact value, we would let n go to infinity. Now similarly, we can use double integrals to calculate the volume under a three-dimensional surface. However, the volume we're going to measure is going to be from the surface of the function, this is our function f of xy, the surface, to the xy plane. And we're going to use three-dimensional prisms, in this case rectangular prisms, which we're going to take a look at below. So if we look down here, we have, if this is the surface I'm trying to find the volume under, I can break up this region in here into littler parts, like right here. I can break it up into rectangular prisms. Now, if we want to accomplish this, we need to find an infinite set of three-dimensional square-based prisms, or rectangular base, and project them from the base of the region R until it hits the surface. If we make the prisms have infinitely small base area, we can get the exact volume under the curve. Again, this is no really different than what we did accomplish last year with rectangles and areas. So in other words, if I want to find the volume underneath the surface, we're going to take a look at the base R, and we are going to project that. Project the base to the surface. Oops. And we're going to calculate that volume. Whoops, can't spell volume. There we go. And we will calculate that volume. So we're going to project the base up until it hits the surface, and we're going to calculate the volume. So this might look a little familiar to you. Well, if I want to find the volume from geometry, we know to get the volume, we can take the base times the height. So let's take a look at the base down here. Well, we can break the base up into littler, tinier rectangles. Now each of these rectangles will have a width, a chain, dy. They will have a little tiny width, delta x, or delta y and delta x. So if I bring that up, now if I raise this one little rectangle up, it will intersect our surface. And I can find the volume of this little tiny rectangular prism. So, and we can see that over here. If this is delta y, and this width right there is delta x, I can calculate the volume of this prism right here if I knew the height, which we do. The height is the value of the function, just like our area last year. So to get the base, well, the area of the base, well, that's just going to be our delta y times delta x. The height is the value of our function at that point, f of x, y. Now remember, this is only an approximation. So to make this more accurate, well, what do we have to do? Well, we have to make the base infinitely small. So we have to then let delta y and delta x go to 0. And if we do that, from calculus, we know we're going to get an infinitely skinny prism. And we can now rewrite our function as f of x, y, our height, times dy dx. Remember, dy dx is the limit as delta y and delta x goes to 0. So this is now the volume of an infinitely skinny prism. And we're going to add them all up. So now the question remains is how can we create a Riemann sum that will approximate the volume? Well, if we assume that each of the boxes has a base area of A. So remember, they're talking about the base area of A. So A, well, that's just our delta y, our delta x, and the height of f of x, y. Then how would we represent the volume of one of the horizontal rows of boxes in sigma notation? What would represent the volume of one of the vertical rows of boxes? Well, to get the approximate for the volume, we would do this. Our integral, our sigma notation, just like our area problem, would be the height of our function times the area of our base. Now remember, A is special for us. A is our change in delta y, delta x, because it is rectangular. Remember, our base is rectangular down here. And notice we have a double sigma notation, one for dealing with the x's and one for dealing with the y's. And that would give us our approximate. Now again, like we said, if we want to get more accurate, well, what do we have to say? Well, if I want more accurate, I have to get my base smaller. To get the actual value, we're going to let A go to 0. And if we do that, we get dA, which we're going to talk about in the next, which we're going to talk about real quickly. So, we can convert this approximation to the exact value by making the area of the boxes infinitely small. And therefore, we're going to get the function right here. By letting A go to 0, get really small, we get dA. And we have this notation. The double integral f of x, y, dA, where dA is the area of the base. That is for us dy dx, could be dx dy depending on the variable. F of x, y is going to be the height of our function, and this little r right here, this is the limit of the base. R is the region of the base. Occasionally a rectangular base, but it can also be in different shapes. We'll take a look at some examples right there. So let's take a look here. Here's what we have. We're looking for the double integral. We're looking for this right here, 6xy squared dA. So what this is asking for us to find is they want us to find the volume under the function f of xy to the xy plane. They want me to find the volume underneath this function all the way measured to the xy plane. So this dA, remember, write this is the region on the xy plane. We talked about that in our previous video. This is our video on the xy plane. Now next, remember this 6xy squared, this is projected on the xy plane. So remember, so we're trying to find the volume using this base right here, because this is going to give you my change in x's, and this is going to be my change in y's. So we're looking at the base region right here on the xy plane projected up to this function, and we're going to try to find the volume. So first things first, let's talk about the base. To get our base, I know my x's are going to go from 2 to 4, and my y's are going to go from 1 to 2. So I'm given this rectangular base right here. And this is our base. We have delta x and delta y. Now I'm ready to go ahead. So if I get the limits for my base, right here, my limits are going to go, my change in x, my vertical, delta y. Well, if I think about it being vertical using a horizontal rectangle, my delta y is going to go from 1 to 2, and my change in x is going to go from 2 to 4. So this is the base we're projecting, because remember, we're going to take this rectangle, we're going to move it right and left between 2 and 4. So to get my volume equation, we would write that as, well, we would have the base times the height. Now we do tend to switch them around because my base is going to be delta x delta y. So because remember my base is this dx dy, or I could write this as the base times my height, which is this 6xy squared. And if I simplify this, this becomes 6xy squared. Now, I'm going to do dy first because I chose a vertical rectangle. I'm going to put it in terms of dy first. We saw that yesterday, dy dx. And we're going to integrate that. Well, my y's are going to go from 1 to 2. And my x's would go from 2 to 4. And this is our integral that will find the volume of this region right here, that surface. So looking at the next one here, again, here's our function, f of xy. Here's my base, this is my base. There's my delta x, my delta y. So if I look at the base of the region, my x's are going to go from -5 to 4, and my y's are going from 0 to 3. So I have this rectangle. This is the region on the xy plane projected to the surface of f of xy. To get the limits, I have to decide, do I want to start vertical or do I want, that's a weird way to spell limits, okay. There we go. To find the limits, I have to decide, do I want to go vertical, start vertical, or do I want to start horizontal? Now most functions in calculus, remember we always start with the vertical because we're in terms of x. So I choose my vertical. So that's going to give me my change in y's. Well, my change in y's goes from 0 to 3. But remember, we are going to move this left and right. And that gives us our change in x, which is going to be from -5 to 4. So I can now write my volume equation as my base times the height. Well, my height is this function, 2x minus 4y cubed. There's my height. And here's my base. dy dx. Now remember, I'm doing dy first because I chose to do a vertical rectangle. And that goes from 0 to 3 for the y's, and I integrate again from -5 to 4. And you could type this in on your calculator, and if you did this, this is a double integral, you would get -756. All right, go on to video number 2, we'll take a look at a few more examples.